this lecture, we're going to look at maybe it's going to be 2. I'd like to go through it properly at a good pace though. We're going to look at the changes to equilibrium graphs again. Let's make a headline here and note. We're going to be talking about changes to equilibrium, right? Changes to equilibrium and its graphs again. And what we're going to be doing is we're going to focus on rate of reaction. Right? Now what did we say? We said that in a rate of reaction graph, I've got it, in a rate of reaction graph and equilibrium, it looked like this. If you remember, this was now rate of the reaction. This is time, and we said at the beginning, as usual, we started off, but now they come together like that. This was at t equals 0. This is the forward reaction. Remember on the previous one, when we spoke about it, this is the reverse, by the way, reaction. And at equilibrium over here, the forward rate is equal to the reverse rate. Now, what we're going to do now is we're going to discuss the rate changes when we actually make a change to the equilibrium. What we do is we've got at equilibrium. Now, just to recap, at equilibrium, it means the rate of the forward is equal to the rate of the reverse. What am I saying? I am saying, if remember our analogy of the boiling water, for every one going out, there's one coming back in. So at that point, that is what we've got. Right? Now, let's have a look at the factors affecting rate. Just to recap here. Factors affecting rate of reaction. Right? Factors. First one is concentration. Right? Remember, we said concentration, if it's high, it's a fast rate. If it's low, slower rate. Right? The next one we said was temperature. Temperature, okay, high means fast rate. Low means slower. Can you see, I'm not talking about reverse or anything yet. Pressure, right? Pressure, high, faster. This is all to do with the Maxwell-Boltzmann temperature, and the pressure one is to do with pressure is proportional to number of moles, and low is slower. Less effective collisions, and last of all, obviously, we're going to talk about the catalyst again. Okay, catalyst, just let's leave this one blank, because we said actually all it does is you get there faster. I suppose we can fill it in. Let's just put in there what I just said. Whoops. We get to equilibrium quicker. Correct? Now, let's just take the graph, shall we? And let's play with it. Let us examine now what happens. Now, when you get one of these, you've got time over here. This is t equals 0. And in this case, let us say that they give us a graph that is there. All right? And this is perhaps not 0, but this is at t equals to 3 minutes already. What can you say? You say, hang on. All they've done is they have left off the first bits. Okay? They have started at let me just write that nicer. They have started it at equilibrium. Right? Just be aware of that. They don't always draw it. So now the one on the top we label as forward, and the one on the bottom we label as reverse. All right? What does that mean? The forward forward was make product. The reverse was make, let me just put it onto the other side, either it's use product or make reactant. Now, if we increase the concentration, right, we are going to affect the reaction, are we not? We said, let's just talk first of all, increase concentration. I didn't say of what. Increase the concentration. Okay. If we increase the concentration, the rate of reaction will increase. Correct? We've said that concentration and tempo, rate of reaction, are related. The more concentrated the acid, the quicker it's going to burn a hole in the kitchen counter. The rate of reaction will increase. But which? The forward or reverse? Which? You must work out. Depending upon what they give you, we can work it out. So let us start with our problem over here. All right, and I'm going to say this is the forward. I'm just going to give a little bit more gas, a little bit more gap, sorry, forward and reverse here. Okay, so what am I saying now? Now I said we changed a concentration. Okay, let's just have a theoretical reaction. In fact, I think I used one. No, it doesn't matter. We can just basically have, we've got, let's call it reactant going to product. Okay. Now increase, we can increase reactant. Okay. Let us first of all increase reactant. What's going to happen? If I increase the reactant, I am increasing this side here. Le Chatelier says that equilibrium will be re-established, okay, at a new level, but what will happen is it will favor the forward, won't it? If I put more reactant in, it's going to favor the forward reaction. Oops. Favor the forward reaction. Right? So it's going to favor that one. This is increasing a reactant, is going to favor the forward. Right? Which means the forward rate is going to go up first. Right? Where's my new level of equilibrium going to be? Above here? Above or below? It's going to be faster. So I'm going to go up to there and down there, and this guy is going to come and join me up there because I have increased the concentration. All right? So this is rate of reaction. You've made it faster. That's the forward, that's the reverse. I have favored the forward. Now, let us do it. That is so terribly frustrating. All right? I just want to fill in my increase there. Now, let us now move it forward. What I'm going to do now is exactly the same graph. All right? Rate here of reaction. T equals, say, 3 minutes, and here's our 2 lines. Always label forward, reverse. Okay? That the forward is on top, the reverse is at the bottom. Now I'm going to say I've got reactant going in equilibrium to product. Right? Now I'm going to increase the concentration of the product. According to Le Chatelier, thus, it's going to seek to remove. In other words, it's going to favor the reverse. And it means I'm going to go that way. So that means I'm going to make reactant, aren't I? I'm favoring the verse because I've increased this. And I am still going to be higher. But what I've done is I have favored the reverse one. Okay? Can you see? Like that. And this one will come up there. Because I made the reverse reaction faster. That was it. I suddenly upped the reverse. Above, I upped the forward relative to the reverse. Okay. Can you see the logic here? All you do is you say, which way did I forward? And then it tells you which one is going to be faster, doesn't it not? So then we could say, all right, what if we decrease the reaction, decrease the concentrations? Well, just to finish it off, all right? Just let's do it once. We're not going to do it twice for this. I've got reactant going to product. All right. And here are my, this is at time equals to 3. This is rate of reaction. Remember, you always look at the axes, hey? This is time. Now, in this case, I am going to decrease a reactant, right? Remove some nitrogen or hydrogen or whatever the case might be. So when I decrease my reactant, the next step is I am going to end up with a what? I have decreased, I'm going to favor the reverse. Favor reverse, which means the reverse reaction, okay? My reverse reaction is going to be speeded up. Or is it? What actually happens here? Here I have removed it, okay? I've decreased it. So my new level is going to be below. So I have changed the rate of the reverse reaction, and I have, this is my forward, that's the reverse. So I change the rate up and we go down, and this one does a thingy and comes down to here. Okay? And I've got my forward and reverse. Over here now what we've got is we're saying that this is lower. It's lower because I have reduced a concentration of a substance. Therefore, slowed the rate down. Right? We've slowed it down. So when I reduce a concentration, my reaction is going to slow down. Okay? For example, I could take away product. It means that, no, well, let's just do it for, that is so frustrating. Okay, let me do this way, do another one. Last one, here we go. Let's take away product. Here we go, here's our thing. This is the forward, this is the reverse, okay? Now I'm going to decrease the concentration of product. Okay? Overall, everything is decreased, so I've taken it away. Therefore, favor the forward. Okay? So I'm going to favor the forward reaction up and then down. The new rate is going to be, goes down and then along, okay? Forward, reverse. And once again, I must be at a lower point because my reaction is slower. My reaction is slower. Going through the same logic, we're now going to look at some of the different ones. Let us take that we have an example and we have a theoretical reaction. I used SO2O2. Well, let's do this. 2SO2 gas plus O2 gas going to 2SO3. Gas, that's a real reaction. Delta H less than 0. All right. So what do we do? Let's look at pressure and temperature. Here's temp. Remember, that's what's going to tell us endo or exo. Immediately we can see this is exothermic, isn't it? The next step is to say, right, for pressure, what do? I say this is 2 moles of gas plus 1 mole of gas. Over here, split it up, 2 moles of gas. Remember, if it's solid or liquid, you don't include it here. Therefore, this is 3 as to 2. This is high, that is low. Remember, that's what we do all the time, right? Now let's have a look. What are we going to do? Okay, let's change the rate of reactions and see what occurs on this one. First of all, okay, let us say we reduce pressure. All right. Okay. Now, step 1 in all of this, okay, step 1 is, let us say we let's increase pressure. Right? So here's my reaction rate graph. This is the rate, this is the time. And let's say at this one we have a situation like this. All right. Now I've got forward and reverse. If I increase the pressure, okay, the first thing that's going to happen is by increasing the pressure, I have increased the concentration. That doesn't apply here because I'm talking forward and reverse. If I increase the pressure, I'm going to change the rate. Am I going to increase it? If I increase pressure, therefore, the rate must go up. Right? Pressure, increase the rate. More effective collisions, which means I'm going to be up here somewhere. My equilibrium is going to be at a higher point, a higher rate. Is it not? Therefore, now I say, right, which one was I favored? The rate must go up, but which rate? Forward or reverse? Let's see. Well, now we go back to our equation and we see, okay, if I increase pressure, I am going to favor the forward. That's if I increase pressure, favor forward. If I decrease pressure, I'm going to decrease pressure. I favor reverse. Don't I? Increase, it'll favor going to the low side. Therefore, if I've got my thing, I say, right, what did I favor here? I favored the forward. Therefore, the forward shot up and goes back to a new pressure. This one comes up to meet it, and this is going to be higher because, okay, increased rate. If I lower the pressure, this will go down to here. If we lower pressure. But what will happen if I lower it? I am favoring reverse, so reverse will drop down more. Reverse will drop down and the other one will come to meet it. Because we work actually with the one that's going to be affected straight off. What happens if I increase temperature? Same reaction, increase temperature. Okay. Therefore, now, remember we're talking temp. We said this is exo. And I said that's forward. Let me just try to write it in too small a space. Forward. Okay. forward, exo, reverse, endo. So now I say, okay, I increase temperature, therefore favor the reverse, because the reverse. Why? Because endo is high temp, isn't it? If I increase the temperature, I'm favoring the reverse in this reaction because it's exo. Remember, you have to do the little sketch. Therefore, what does my my graph look like? I go and I say, okay, let's draw it. And we had it here, and you go there, and you go here. Now I'm going to, at this point, T over here, it's at equilibrium. I label forward, reverse. Now what do? I am favoring the reverse, therefore the rate of the reverse is going to go up. Okay, higher, increased temperature, therefore rate of reaction goes up. So you look what you did and you look what's going to happen to the rate, then come and say, okay, the reverse reaction was the one, and then put the other one up to it like that. Okay? Simple, isn't it? There you've got your reverse, and now you've got your forward. The forward has come in underneath. Of course, they can cross, it's no big deal. What you've got here is you've got the reverse reaction was the one that was favored. So the first thing we did is the reverse reaction's rate went up, and then eventually the other one caught up with it, didn't it? Right? So when we are looking at these, what we've got to do is we've got to say, what is happening? Okay? Let us take same one, and we now going to say, right, decrease pressure. Okay? What did we say? We say, okay, step one, okay, we are over here. There we are. We're here. Now we're going to do something. If I decrease pressure, rate must drop. So immediately I know I'm going to be down here somewhere. It's dropped. Slows down. This is rate of reaction. We say it slows down. We know it's going to slow down, don't we? Therefore, I immediately know it's going to be below. My next question is to say, okay, by decreasing pressure, which was favored? So I go, okay, let me just complete my sentences. Which was favored, forward or reverse? And I need to go to the equation to answer that. And I say, all right, here's my equation. Okay. We dropped the pressure, therefore we favored reverse. We're favoring the reverse reaction. Okay. We are favoring the reverse reaction. And now I go back to my graph and I say, okay, I've decreased pressure. I'm favoring the reverse. I've got a label. So immediately my rate of the reverse goes up, but then drops down here like this. And this one comes to join it over there like that. This is the forward. Sorry, my bad. I favored reverse. Sorry, I drew it incorrectly. Sorry. So let me change color here, shall I? I favored reverse, and it must come lower. So it's going to do that. And the forward reaction is going to basically come down to join it like that. All right? There's my reverse and there's my forward. So I went and I found the one that I needed. The one I needed was the reverse because I decreased pressure. Last one. Now we're going to go and we're going to decrease temperature. Decrease temp. Straight away it's temp, so I go and I draw my curve and I label it forward is exo, reverse is endo, and I say what? Decrease the temp, right, here's my graph. The first thing I ask is I say, okay, there we go, forward and reverse. And this is where I make my change. I'm going to do it in blue. Maybe I should have done them all like that. My apologies for not doing it in color. So I say, okay, decreased temperature means the rate is reduced. So I know it's going to be in here somewhere. It's going to be lower because it's cooler. Now I say, therefore, which is favored? Forward or reverse? It's a bit like gears on a vehicle, isn't it? Forward or reverse. So I say, all right, how do I answer that question? I go to my thing. If I cool it down, I favor the forward. Therefore, my forward rate goes up and then drops down. And this one then comes in to join it. Forward and reverse. Like so. The last thing we have to say is, what does the rate look like if you put a catalyst? This is a catalyst. This is the easiest one of the lot, and it's a good one to spot. Here we go. All right. Label forward, label reverse. Okay. Okay. And darn, come here. Okay. Forward and reverse. All right, do this. And basically, the equilibrium has just gone up to that point because a catalyst favors forward and reverse equally. All you've done here is you've increased the rate of the reaction. You've increased the rate of the reaction. That is what we've done on there, like so. Okay. Thus, on the graphs, what do? We look and see if it's a rate. Okay. We know that increasing pressure, concentration, or temperature, forget catalyst, those three will increase the rate. So immediately you know the rate is going to be higher. The next step is to say, did it favor forward or reverse? That's the line you're going to use as your first kick. So if it favors reverse, it's the line underneath that goes up first, and it goes and joins there, and then the forward will join it. I think the process is fairly clear of what to do with them. They are very straightforward actually, and you just got to remember the catalyst is basically just both of them go up. That's the easy one to identify. Thanks for watching. I hope that the graphs make a bit of sense. I know that they can be fairly tricky to try and work out. A lot of people try and work them out from first principles, but what we did is we just said what's going to happen, up, down, and then identify which one was favored. That's all it is. Therein is the key. We've got to know the previous section of work pretty well to say, okay, there's that, and that. And remember always, when you're talking about which is favored, you have to state according to Le Chatelier, okay? That's a fundamental prerequisite for it. Cheers, thanks for watching. Next section we're going to go on to is equilibrium constant, Ka, Ksp, Kc, a few of those. Cheers, I'll see you then. Bye.